video, we came up to the schematics. Now we will move on to the test benches. So in this process, add source file. Then you have to go to add or create a simulation sources. Then you have to do next. Then you have to give a create file. Then be specific that you have to do VHDL. Then apply half adder TB. There, this is for the test bench. Then OK and finish. Okay. So this is the all things that we need to do. So you have to do yes. And now in the simulation sources, there is a TB file. Then you have to go in the half adder TB behavioral file. Then a library is used, which is a standard library for VHDL. Okay, so and the STD logic stores the data types such as 0, 1, Z, and X. So without this, VHDL will not understand the ST logic. Okay, STD logic. So IEEE and STD logic library provides a standard logic data types for digital designing. Then we have a test bench entity. So in the test bench entity, test bench is a not real hardware. It only tests the design internally. The test bench entity has no input and output ports. Okay, and the behavioral. Then we will move to the architecture behavioral, in which the behavioral means we describe how the test behaves. It is a non-synthesizable. It is only for the simulation. Then component declaration (DUT). So what is basically a component? It is a copy or a blueprint of your actual design. It is used to instantiate a design inside the test bench. So ports must exactly match to the original design. So here we have defined the ports such as A, B, S, C. A and B will be the input, and S and C will be the output. So component declaration allows the test bench to access the design under test. Then there is a signal declaration. So why this signal declaration is used? Because the ATB will be as the test input A and BTB will be test input B. STB will be observed sum and CTB will be observed carry. These signals acts as wires between TB and DUT. TB means test bench, okay? Then we will move ahead with a begin statement. So this marks the start of an executable code. Then there is a DUT instantiation. DUT means design under test, which instantiates the actual half adder. Okay, so there is a port mapping in this. So A is mapped to ATB, B is mapped to the BTB, and etc. So the stage bench drives. These are the test bench drives, which are ATB and BTB. This processes logics and outputs appears on the STB and CTB. Okay, then there is a stimulate process. Then it is a sequential blocks which executes the statements one after another. Okay, then there is a test case execution. So there are total 4 cases, like A 0, B 0, A 0, B is 1, and further. Okay, so why we have used here wait, which allows the time signal for the signal propagation, makes waveform clear and readable. And in the last we have used wait, because to terminate the program, to stop the process, and it shouldn't go into the infinite loop. So we have used here wait. Okay, so and end is the end of the program. Then we save this file. After saving the file, so here synthesis is complete. So we have to go in the simulation. So when we go on the simulation, so there when we clicked on the run simulation, there is a run behavioral simulation. So when we click on this, so it is analyzing. So this what we get after we do the run simulation. So these are the files added. These are the signals which are added to the waveforms, and this how we get the waveforms. Okay, so this is how we get the waveforms. So when this is the logic applied to it, so now we will go to add a, like the next step is to add a constraints. This is used to import this code into the export this code into the FPGA board. So again we have to go to add sources, then we have to go add or create constraints, then here we have to go for create file, then this file must be XDC, which is a Xilinx design constraint. Then again we will give a name. Okay, so I have given this name. We will keep the same location and finish. So now we will create the, sorry. Okay, now we will create the constraint. So we can see that here is a constraint which is one available. So the file we made, now we will upload a code for the constraints. Now for the hardware implementation, we have added the constraints. This port A and port B is connected with the L5 and M5 of L5 and M5 pin of the FPGA board, and port S and C is connected to the pin J3 and K3 of the FPGA board. Now we will save this file. Then we will go for the run implementation to implement this. Then we will yes. Okay, it will take time. See, you can see here that it is happening here. So after this, click the generate bitstream option. This option is used that bit file is transferred into the FPGA board, which will be then run by the FPGA. Okay, so here I don't have the FPGA board, so this is the last step up to which I have shown you how to implement the half adder into the Vivado software. These are the all steps which are included in the VLSI programming and designing techniques. So I will summarize that what we performed in these two lectures. So we created a project of half adder, then we writed a code of RTL inside the VHDL of the that how the half adder is going to perform. Then we form the schematics, that how the schematic diagram of the half adder will look. Then we created the source file for the stimulation, and we wrote the test benches for the stimulation. So in that, what are the test benches, how they performs internally. Then we made a stimulation in which there is the run behavioral simulation. Then we got the timing diagram, so we can analyze that our circuit is right or wrong. Now the all this after all this we have done, we go to the run implementation and generated a bit stream file. This bit file is then uploaded to the FPGA. So we do open here, open manage hardware manager. I don't have the FPGA board, so here FPGA, you have to connect the FPGA board to the laptop, and then you have to upload this file into the FPGA, and then FPGA will work according to your requirements. Okay, there are the few connections which have been made further for the hardware implementation of half adder, but this video series is only for the software implementation. So we have completed our half adder in the Xilinx Vivado software. These are the all steps including front end and back end of the VLSI technique. Thank you.